questions in the chat, and you can take a look periodically, and we can defer most of the questions to the end also. Whatever you feel comfortable with.
So if there are questions, if at the end of a section of my talk, if there are questions relevant to that section, I can answer so that the question got answered in time, right?
Sure.
If it's a more general discussion, I can postpone to the end.
That sounds good.
Yeah. But in case I don't see the questions in time, could you help me?
I'll interrupt you.
Yeah, cool. Thank you very much. Hi, good to see you.
Hi, Chi. Yeah, thanks for coming here.
Yeah, thanks for inviting. It's very exciting.
This is the autumn break, the first day of the autumn break. So I'm not sure what does that mean for the talk. Is that people are out, or is like people have more time to attend the talk?
I see. So how long is the autumn break?
Just these 2 days, and then plus the weekend. So it's a long weekend.
Oh, got it. Yeah, so people might have plans going out.
Yeah.
Yeah. So how is everyone doing? Life back to normal?
Yeah, I think that everything is almost normal now. Everything is in person. We've still got some cases here and there, but yeah, generally, I think things are just so much better in person.
Yeah, happy to hear that.
How about Microsoft? Is that everything?
So we're in the full stage of back to normal on campus, so people can return to work just as normal. And we are also okay to work from home for like less than 50% of time, unless there are some special requirements. Yeah. So my observation is like not everyone has been back to office normally, but usually they will go to office like a few days a week, things like that. They will occasionally drop by my office, but it's not fully occupied space, still quite sparse. Yeah.
Okay, so I think we have some critical mass here. Might we will get started just in the interest of time.
Yeah.
DK, should we record this?
Yeah, I think Nilima has already started.
Oh, right.
Yeah, we have permissions from Dr. Wang to record. Yeah, I've already started the recording.
Thanks.
Okay, good afternoon to all of you in the East Coast, and good morning to others in the Midwest and Pacific. It is our great pleasure to have Dr. Chi Wang from Microsoft Research giving us a talk in our ICICLE seminar series. So just to introduce Dr. Wang, he is a principal researcher in Microsoft Research at Redmond. He received his bachelor's degree from Tsinghua University and completed his PhD at the UIUC, advised by Professor Jiawei Han, where he won the SIGKDD Dissertation Award. And his research is centered around the interplay between theories and systems related to data platforms and data science. And Dr. Wang pursues fast, economic, scalable, and practical solutions with theoretical guarantee. His research has led to a lot of life-changing technologies for data scientists and engineers. He has built this FLAML, which he will be talking today. And it is very widely used inside and outside Microsoft. For example, Visual Studio, Azure Data, and Microsoft 365. I mean, many of us might be using that without even knowing that it's Dr. Wang's contributions have gone into that. So with that introduction, I'd like to again welcome Dr. Wang. Please, the floor is yours.
Thank you so much, Dr. Ben, for the introduction. Okay, hello everyone. My name is Chu. I'm a principal researcher from Microsoft Research. It's my pleasure to introduce the technology my collaborators and I invented for fast AutoML and tuning, and the library we built using the technology. Here's the outline of the talk. I will first give an overview of FLAML and then talk about the hyperparameter tuning and AutoML techniques, respectively. I'll mention the impact and future work in the end. So feel free to ask questions anytime during the talk.
Yeah, just a note, if anybody wants to ask questions, please post it in the chat and Dr. Wang will take a look at it periodically, or I can interrupt him. Okay, and more general questions, we can leave it to the end.
Yeah. Thanks.
Thank you. Bye.
Thank you. Yeah. So recently, McKinsey identified 7 cross-industry trends that reshape the future of markets and industries in the next few decades. And 2 of them are related to applied AI and the future of programming, also known as software 2.0. A growing number of developers now have access to AI and machine learning techniques, and there's a strong interest in using them. The mission of my collaborators and myself is to help them master AI and machine learning operations to make the most of both trends. Under the operational context, let's take a look at the general machine learning workflow. To use machine learning in an application, we need to get the data for that application, prepare the data, train the models using the data, and evaluate the models. Eventually, the models will be deployed and consumed as a software component. Before the models meet the deployment criteria, the model developer, for example, a data scientist or engineer, keeps iterating the model training. There are a lot of decisions and choices to make for a general developer to find a good model. For example, they need to choose a right machine learning model well implemented in the machine learning library to perform the training for their data and their task. There are many machine learning libraries like scikit-learn, XGBoost, LightGBM, PyTorch, TensorFlow. Each of them offers many knobs to tune to optimize model performance. For example, for LightGBM, which is a library for gradient boosted trees, we need to choose the number of estimators, number of leaves, learning rate, etc. When we use the wrong setting, we could easily see the accuracy drop from 90% to 50%, making the model unusable. Choosing the right combination of learner and hyperparameters for a new dataset is really a trial and error process. Also remember, it's not just a one-time effort for one application. Every time the code, data, or deployment criteria are updated, the choices could become invalid and the optimal configuration could change. And even with a huge effort of manual tuning, very often the decisions made are still suboptimal and significant model performance gain opportunity is left on the table. AutoML tools are built to automate that process, to remove the hassle of manual tuning for data scientists and engineers, so that they can focus on other issues. Some of the tools empower developers who don't necessarily have expertise in machine learning. We have seen a rapid growth in AutoML software, including open source, cloud providers, and startup companies. The market size forecast in 2030 is about $15 billion. What kind of AutoML tools do users really need? Based on our interaction with customers, there are several important requirements they desire. For example, they desire AutoML tools to make them more productive with affordable cost. One common complaint of AutoML tools is they often consume large computational resources, especially for large-scale training data. That causes system failures, meaning the system is not able to return a usable model. Many users had to run experiments on limited computation resources, and they had to modify the model search space to reduce the total runtime. Some users would even revert to manual development for large models, which is a big setback in terms of productivity. Another important property is about customizability. On the one hand, it's necessary to provide enough customizability to target diverse requirements. On the other hand, if the tool requires too much effort in making many hard choices for users, it goes against the purpose of AutoML. Sometimes a user would say, I only want to customize 1 or 2 things, and I want the library to decide the rest for me. most existing tools fail to meet these requirements. So we designed FLAML, an open source library for AutoML and tuning. It strives to be fast, economical, customizable, and extensible. We build a high performance, robust tuning layer, and then we build the AutoML layer transparently on top of it. The machine learning component uses existing machine learning libraries as black boxes. FLAML enables a smooth customization experience, all the way from the most automatic AutoML experience to the most flexible tuning experience in the same library, covering all the middle grounds. For example, task-oriented AutoML is a high-level AutoML API suitable for all the users, no matter whether you're an expert or a beginner. It can be used as a scikit-learn style estimator in just 3 lines of code. It requires minimal input. You only need to specify training data and task type to use it. Customizing the optimization metrics, learners, and search spaces, etc., is very easy. For example, you can add an argument in this fit function here. Let me change. Yeah, so this one to restrict the learners or add a custom learner. There are other scenarios where you want to use a different API to run generic hyperparameter tuning for a fully customized function and search space. For example, when your machine learning task is not one of the built-in tasks, or when you need to directly optimize the performance for downstream application. All the use cases are fundamentally powered by our hyperparameter optimization technology. I will talk about it in the next 15 minutes. And after that, I will talk about the extension to AutoML. Any questions so far? Okay, so we're good. Yeah, so for hyperparameter optimization, I will mainly talk about the first paper listed here and briefly mention a follow-up work. They are joint work with my former intern, Zhengying Wu, who is now professor at Tsinghua University, and my colleagues Silu and Amin from Microsoft. HPO is an optimization problem. Given a large search space of hyperparameter settings, we target optimizing for some loss function in the validation data. For example, when using LightGBM, when you fix these hyperparameter values, X, you can run the complex black box training process to evaluate the validation loss F. You can observe the value of F for each given X, but you can't compute the gradient of F with respect to X. So that distinguishes the HPO problem from the typical optimization problem in machine learning and makes techniques like gradient descent inapplicable. In general, we need to repeatedly invoke this machine learning training black box using different trials of the hyperparameter settings. Each invocation incurs a non-trivial cost. We use G of X to denote the cost for training and evaluating configuration X. Both the loss F and the cost G are only observed after a trial is finished. The total cost of optimization is the sum of the cost for all the trials before the optimal configuration is found. Its total cost can be very large because of 2 contributing factors: the large number of trials and high cost per trial. It may take hundreds to even thousands of trials before the tuning stops, and each trial can take hours on large data sets. We propose a new cost-frugal HPO formulation to find the configuration with lowest loss using small total cost. Under this formulation, and if the cost G of X is constant, the HPO algorithm only needs to make the number of trials small. Most of the existing work, for example, Bayesian optimization, is devoted for this scenario. But in practice, it's common to encounter hyperparameters which affect the cost significantly. For example, in this heat map, we demonstrate the cost variation for training XGBoost using different configurations of 2 hyperparameters. The training cost can have 10,000 times difference between cheap and expensive configurations. And the research question is that with cost-related hyperparameters, how shall we do HPO at low cost? Previously, there was no rigorous study about this problem. Intuitively speaking, we need to design algorithms that can avoid high cost and high loss points. As we mentioned, since the loss function is a black box function, it's difficult to know which points have high loss a priori. But it's reasonable to assume we have a little knowledge about the cost function. We observe that the cost is usually Lipschitz continuous with respect to the hyperparameters, like this figure shows. And we already know some configurations has low cost before we start the optimization. For example, the configuration with minimal number of estimators and leaves. How to leverage these observations? The first intuition is that to avoid high cost points until necessary, you can start from low cost starting points and use local search. And second, in order to find low loss points, we want to follow the loss descent directions. But we hit the blocker right here. Remember that we can't directly use gradient-based methods since no gradient is available in general. So many people think that the idea of local search will not work. That's why global optimization techniques like Bayesian optimization are the mainstream methods in HPO. But we're going to challenge that belief. We will show that if you do the local search in the right way, it works without knowing the gradients. Using function values is good enough. We propose a very simple and effective algorithm. What's even more surprising is that our algorithm doesn't even need to know the function values. It only needs to know the sign comparison between function values. Can you believe it? I will give everyone a few seconds to imagine how it can work. Okay, so here's our local search method. It's called flow square. I will use the animation to demonstrate the core idea of this algorithm. To better visualize our method, I will execute our algorithm using the loss heat map as the background. Remember that the algorithm doesn't know the value of the loss until it tries a particular point and evaluates it. Our algorithm starts from a particular low-cost starting point. At each iteration, we uniformly sample a direction from a local unit sphere. And then we do the evaluation and compare the loss. If it improves, we move to this new point and start a new iteration. And in the next iteration, we start over and repeat the same at this new point. So basically do another round of local random sampling and do the comparison. If after the comparison, we find the loss is not improved, we will try the opposite direction. And then decide whether to move or stay. If the performance is improved, we'll move to this new location and repeat the procedures again. This process has the following implications. First, the incumbent, which is the current location, has the best loss. In this animation, the black dots are the incumbents. The evaluated points in the next iteration are in the neighboring area of the incumbent. It further indicates that the cost is not far away from the incumbent. Let's see the full animation in the loss space. In this animation, the black dots are evaluated points by the algorithm. And the dots connected by lines are points that yield better performance. The trajectory on this heat map shows that we can indeed navigate the points with low loss efficiently. We provide theoretical guarantees on the convergence rate of this algorithm. The convergence rate is comparable with that in stochastic gradient descent with a constant step size. This result is non-trivial because we don't have the gradient information during the optimization at all. The heat map on the right-hand side shows the trajectory in the cost space. You can see that our algorithm can indeed avoid the unnecessarily high cost region, like this part. We also provide strong theoretical guarantees on the total evaluation cost, which is the first of its kind in the HPO literature. You can find all the proofs in the full version of our paper. Comparing our method with existing optimization methods, we have guarantees on both the loss and cost, and it's applicable to black box functions. None of the existing methods have bound on the cost. We further make several practical adjustments to convert FlowSquare into a off-the-shelf HPO method. We name the final method as CFO, which stands for cost-frugal optimization. We design our solution to be self-adaptive, so no tuning is required from the user. We compare CFO with other representative methods in several categories. Random search and Bayesian optimization are most well-established baselines for HPO, although they don't handle the notion of cost. Multi-fidelity methods make a special assumption about the cost, but it's not designed for generic cost-related hyperparameters. PPEI-PS extends PPEI to handle the cost generically in a heuristic way. It discounts the model's expected loss improvement by another model predicted cost. It's not guaranteed to outperform PPEI. CFO0 uses the same framework as CFO and replaces FlowSquare with Netzerov's zeroth order method. This zeroth order method wasn't ever used for HPO problems. We included here to verify the effectiveness of FlowSquare. Let me check the question. This question from Rajiv. Rajiv, if you want to ask directly, feel free to speak. Otherwise, okay. I can read the question. Yeah, go ahead.
Sure. I can just read out the question. This method, looking at that diagram and that picture, it seems to assume some kind of locality with respect to the loss distribution. In other words, if there is an area of low loss, then there'll be other areas with low loss around it. There aren't like discontinuities in that space. Is this statement correct? And is this generally true?
Yeah, very good question. So this is a very important clarification I want to make. So we don't assume the locality with respect to the loss distribution. We only assume the locality with respect to the cost. So if we go back a few slides, so if you look at these two different heat maps, the first one is on the loss, right? The one on the left is about the loss heat map. The one on the right is about the cost, right? So we only assume the locality on regarding the cost distribution. So if you look at the figure on the right, it's kind of satisfying that assumption. So that's a good question. Yeah. Okay. Sounds good. Let's move on.
Maybe I can ask a follow-up question related to that. I was thinking about the same thing. It's satisfying to know that you only make the continuous assumption on the cost, but could you give more intuition about the proof? Like intuitively, if you have such local smoothness in the loss space, then such local greedy search makes sense. But so what's your proof structure to relax?
So that's another important clarification maybe regarding the convergence theoretical guarantee. So what kind of guarantee we can make? So our proof is about this. So if it depends on the function, the ground truth of the loss function. If the ground truth of function is convex, for example, right, that's the most ideal case, then we can prove this convergence to a global optimum, right? With this our special convergence rate similar to stochastic gradient descent. And if the function is non-convex but satisfies some smoothness assumption, we can still prove the same convergence rate to local optimum point. But as you know, for non-convex case, the local optimal is not going to be global optimal. So in order to find global optimal, we have to restart the search from a different starting point and converge to a different local optimal, that kind of strategy. So that's why we had this several improvements here, right? To, for example, escape local optimum and dynamically change the step size to make it work better in practice. Yeah, so these are the empirical information. We have even more extensions to address that complex search space issue, and I will talk about that after this section. Yeah.
So may I have a follow-up question? So what's the difference between cost and the lost function here? So
yeah,
like is that guaranteed that if the cost is lower, then we get lower loss? Basically what's the intuition there?
Yeah, a very good question. So the loss is about the validation loss of your machine model. Usually it's a metric regarding the accuracy, right? That like 1 - accuracy, for example. But the cost function is regarding the training cost for the model. So there's no fixed relationship between cost and the loss for general data sets, right? For some data sets, you need more expensive model to achieve low loss. For some other data sets, you only need low complexity models, right? So there's no fixed relationship we assume between these two. But the bound regarding the cost, the total evaluation cost, indeed requires some local assumption about how the cost varies surrounding the local optimal point in terms of loss. So for example, we assume that if you already reach the optimal point, right, and then if you further increase the cost, then within a local neighboring area, the loss drops. So that's the kind of assumption we need to make for the bound for the total evaluation cost. But in general, it's that we don't require, for example, higher cost correspond to lower loss or that kind of assumption. That's something we don't assume.
Thank you.
Yeah, great. Yeah. Okay. So let's continue the presentation. So we just talked about there are several methods we compared, and let's see the experiment results. So we use 43 classification, regression, benchmark data sets. They have a wide range of scales. All the data sets are publicly available on AutoML. We perform tuning for 9 hyperparameters of XGBoost and 5 hyperparameters of a neural network, respectively. Let's first look at the results for XGBoost. We visualize the performance curve in terms of validation loss of all the methods over a 1-hour wall clock time period. The loss is measured by 1 - AUC for binary classification, log loss for multi-class, and 1 - R² for regression. We run each method for 10 times and plot the average score and standard deviation. The closer to the bottom left, the better. All the methods start from the same low-cost initial point. The black line is CFO. For all these different types of tasks, CFO has a leading performance. It achieves up to 3 orders of magnitude to speed up compared to other methods for reaching the same loss level. And the same is true for the DNA experiment. By the way, I'm only showing a few examples, but you can, in the papers, you can find all the evaluation results. It's consistent across data set. And although our local search method has both good theoretical properties and strong empirical performance, it also has limitations. Like you asked earlier, when the search space is complex, the conditions required for the local search may not hold for the entire space. So in a follow-up study, we further extend CFO to combine the strengths of local search and global search. The extension is named blend search. We can use Bayesian optimization to add more exploration to local search. Look at this figure. It plots the best loss found by different methods over time in a large search space, which contains several disjoint subspaces. Okay, the blue line is BO, the orange line is local search, and the black line is blend search. The diamond markers, like these, are the trials suggested by BO during blend search. In the beginning, blend search works just like local search. Later on, local search slows down. Blend search keeps improving as BO helps with finding better start points for local search. These colored circles correspond to different local search threads in blend search from different start points. Within each subspace, local search performs well, but blend search has a better ability to explore different subspaces without waiting for one local search to converge. This slide shows our design. We maintain a pool of search threads. This one. There's one global search thread, thread 0, and there can be multiple local search threads corresponding to different starting points. We mark the key components in orange color. One key component is the search thread selector. It's responsible for choosing one search thread and invoke the corresponding search strategy for each iteration. When global search proposes a configuration, it needs to go through a config validator to make sure we don't evaluate a very expensive configuration too early. Otherwise, we will lose the benefit of cost control by local search. After we evaluate the configuration, we'll update the search threads and reprioritize them based on the result. So that's down here. If the configuration is proposed by global search, we'll also check whether its performance is good enough to create a new local search thread. Right? That's this part does. The details about how we implement each component can be found in the paper. One nice feature of blend search is that it's naturally parallelizable, as the different local search threads are largely independent of each other. Okay. I want to mention that our HPO methods can be used beyond tuning a machine learning model. We can tune generic hyperparameters for machine learning workflows, pipelines, mathematical statistical models like causal models, algorithms such as reinforcement learning policies, computing experiments such as simulations, and so on. So, so far our biggest success is in AutoML, but there are already use cases of FLAML beyond AutoML, which verifies its general usability. It has a big potential in other fields. So yeah, so that's the end of this section. Is there any question? Are there more questions about the hyperparameter optimization part?
Yeah, hi, I have a question.
Yeah.
So is there any theoretical study on, to provide a guarantee that the hyperparameter we searched within the time budget will lead to convergence in the end if we finish the complete training phase?
Yeah, so that's I guess the question I answered earlier about the theoretical guarantee. So is there any specific perspective of the convergence that's different from the convergence guarantee I talked about earlier?
No, my question is really just like with this like limited budget training, for example, in an hour, right? I mean, we only like sample
I see.
A fixed number of combinations of hyperparameters and we select the best of them, right?
Yeah.
And how can we guarantee that, later on during the training phase, those hyperparameter combinations are still the optimal ones though?
Got it. So I guess you're talking about the dynamics of like trainings, right? So you're talking about should we use like fixed hyperparameter value from the beginning to the end of the entire training process, or shall we vary the hyperparameters during the training, right?
Right. I mean, are those hyperparameter combinations that look promising in the early optimization stage still the best ones in later on training, right?
Yeah. Got it. Yeah, so this is very interesting question, especially for the deep learning kind of models, which people often use like varying learning rate etc. So a couple of things I want to mention. So first of all, the type of hyperparameters we can tune is very generic. It includes both the kind of hyperparameters that can vary during the training, like learning rate. It also includes the type of hyperparameters which can't be changed. For example, the number of epochs or some neural architecture hyperparameters, right? So those have to be fixed in the beginning before the training starts, and you can't vary during the training. But there indeed exist hyperparameters like learning rates you can change. So how to deal with those dynamic hyperparameters that can change during the during the training process? So one way is to make that dynamic also parameterizable, right? So for example, people often use learning rate schedule, like decaying learning rate, right, starting from some high value and then reduce it later. So you can, for example, make that decaying schedule also tunable, right? You can control how quick to decay and so on. So that's one way to convert it to yet another hyperparameterization problem. That's actually what we did for some large language models fine-tuning problem. And if you want to be even more like flexible beyond that, you need to do some kind of online optimization, right? So now you don't even have a parameterized schedule beforehand, but you want to try arbitrary kind of different schedules. Yeah, there are techniques to do that, but so far I don't see any theoretical analysis yet, right? Just to show this is the best way. But we do have some work related to that in the online learning scenario. So it's for different contexts, but that technique, and by the way, we do have theoretical guarantees in that work to prove that the total regret, the cumulative regret in the end, is not much worse than directly using the best ground truth of the hyperparameters. So that can be potentially used in this in the scenario you described, and have some theoretical argument, but there's no existing work.
Okay, cool. Thank you.
Great, thank you very much. Yeah, I'll briefly mention that online AutoML work near the end of the talk. Okay, so if there's no other question, let's talk about AutoML now. The first paper here described how we extend our HPO solution to a full-fledged AutoML system. It's a ML6 paper done together with my colleagues Cheng, Marcus, and Eric from Microsoft. I'll also touch a little bit about more recent work done with intern Mo Kiali from University of Washington. An AutoML system involves a bigger optimization problem over more factors than the hyperparameters of each specific learner. The additional factors include the learner, the size of the training data, and resampling strategy. Following the same design principle, FLAML optimizes for low computational cost in finding accurate models. The main idea is still to design an efficient search order to control the overall trial cost before finding low error models. The ML6 paper talks about how we consider the joint impact of all the factors in the trial cost and the model error. I won't go into the details. I will just use this picture to outline the system. Given a machine learning task and a particular resource budget, the goal is to find a model with the best performance within the provided resource budget. Here, a task is a machine learning task, including the training data and the task type. For example, regression, classification, etc. The components in blue are modules about AutoML, and the components in gray are modules about machine learning. The system performs multiple trials of tuning and model building within the specified resource budget. Each trial involves one set of learner selection and hyperparameter selection. Then with select the learner and hyperparameter configuration, it trains the model, evaluates the model on the validation data set, and reports the validation loss. The hyperparameter optimization step is empowered by our cost-frugal hyperparameter optimization algorithm I just mentioned. And sample size is treated as a special hyperparameter. The resampling strategy is automatically decided according to the data size and time budget. By the way, FLAML does task and learner level data preprocessing, though the preprocessing step is not shown in the figure explicitly. This slide gives an example of a simplified search sequence, so we can get an idea how the search works. Every iteration will choose one learner, one configuration of the learner, and the sample size. Here we have 3 learners, XGBoost, LargeGBM, and Random Forest. In general, the error decreases as more time is spent for each learner. For each learner, the search always starts with the smallest model, and the training can finish in a very short time. For example, LargeGBM starts with 4 trees and 4 leaves, and the training takes 30 milliseconds. The model complexity quickly increases in the geometric step. So we see that within 4 seconds, the complexity for LargeGBM already grows from 4 trees and 4 leaves to 600 trees and 20 plus leaves. Here. In general, more iterations will be spent on the most promising learner. In this case, even though initially Random Forest has the lowest loss, LargeGBM's loss decreases faster and more iterations are spent in LargeGBM. When increasing model complexity doesn't improve the loss for learner, we increase the sample size. For example, for Random Forest at iteration 23. So I hope you get a rough idea of why FLAML is efficient. There are mainly 3 benefits of task-oriented AutoML. First, it can save manual efforts, including both the effort on gluing everything together and the effort on manual repetitive tuning. FLAML has multiple built-in machine learning tasks you can directly select from. Classification and regression for tabular data are the most common task types. We also support time series forecasting and NLP tasks. For each task, there is a set of built-in learners in FLAML as the candidate learners. The learners are from popular machine learning or deep learning libraries. Second, you can use small computational resource to find models with good performance. Extensive evaluation of the AutoML benchmark also verified the performance advantage of FLAML. These box plots shows the performance difference between FLAML and several other libraries under different resource budget. The possible value means that FLAML is better than the compared alternative. It's worth mentioning that prior AutoML solutions mostly rely on meta-learning to improve performance. Meta-learning tries to leverage tuning history on other datasets, but requires evaluating certain performance metrics of many configurations of certain learners on many datasets as expensive preparation step, and has limited customizability once the preparation step is done. FLAML can achieve better performance without meta-learning, which makes it possible to do flexible customization. That's another notable advantage of FLAML. Allowing easy and rich customization is helpful in scenarios where, due to business or deployment requirements, practitioners need to use a special machine learner, custom metrics, or certain constraints. FLAML is able to support these needs while maintaining performance advantage. Here's a concrete use case from the security domain, where this user wants to use special classifiers to create suspicious behavior detectors in a corporate level security product. The classifiers are not included in FLAML's AutoML learner candidates, and she wants to use a special metric to do the optimization. In this case, she needs to add a custom learner and customize the loss metric. Allowing user-defined metrics in FLAML has great practical importance because it closes the gap between the loss function we optimize in machine learning and the final application metrics we really want to optimize. Users like FLAML because our AutoML solution is generic and metric agnostic, and it performs well out of the box without requiring expensive meta-learning. But when you do have resources to perform the expensive evaluations needed by meta-learning, we offer a simple and effective meta-learning approach in FLAML to further push down the AutoML cost. Instead of running full hyperparameter tuning from scratch every time, one can leverage the tuning experiences in similar tasks before. For AutoML providers of a particular domain or organization, they can learn and customize defaults for users, tasks, /learners, /metrics, based on their own tuning experiences. Based on meta-learning, we built an interesting new feature called zero-shot AutoML. It offers a seamless way to leverage AutoML for the commonly used classifiers and regressors, such as LGBM and XGBoost. For example, if you're using LGBM.LGBM regressor as your current learner, all you need to do is to import the LGBM regressor from FLAML.default. Then you can use it just like the original LGBM regressor. Your other code can remain unchanged. And when you call the fit function from this new regressor, it will automatically instantiate a good data-dependent hyperparameter configuration for a dataset, which is expected to work better than the default configuration. As an application of the technique, we studied in this recent work whether the recommended zero-shot configuration is better than the library default for popular and mature learners such as GBM, XGBoost, and Random Forest. Each learner has offered the default configuration, which is supposed to be robust across tasks, as they have been adjusted by the library maintainers through many iterations of development cycles and widely used and testified for many applications. We investigated the 10-fold cross-validated R-squared score for LGBM on 37 regression tasks. For this score, the larger the better, and 1 is for perfect prediction, and 0 is for constant prediction with mean. So our results are quite promising. The recommended zero-shot configuration consistently outperforms or equalizes the static default configuration. The margin is large in quite a few tasks. On over 67% of the tasks, we observe more than 1% difference in R-squared score, corresponding to significant reduction in regression error. The static default from LGBM performs catastrophically in some tasks like Brazil houses and poker. The zero-shot approach stands strong in the worst-case performance. Remember that the negative score means it's worse than constant prediction. The only case where the recommended zero-shot is worse than the static default is on the task commit, where the R-squared scores are within a 0.5% margin. Okay, so we're near the end of the talk. Any question about the AutoML part? Okay, I will move on. Here's a picture to summarize a few research technologies invented in FLAML. We begin with inventing a simple and provable local search algorithm called FlowSquare. With that, we developed a cost-frugal optimization method, CFO, which has superior empirical performance. That's the core hyperparameter optimization method of the library. The main advantage compared to other HPO methods is that it can use small computational cost to find a highly optimized model. We further extended it to combine with global search and make a framework called Blend Search. It's able to handle more complex search space well and is suited for parallel tuning. For tuning online machine learning models, we developed a technique called char, which I didn't talk about in this talk. It's published in ICML last year. It also leverages CFO as a submodule. And by the way, FLAML is the first and only AutoML library that supports online machine learning models. And this is the work I would suggest Jiao to take a look at regarding the like how to tune the hyperparameters online. And recently we invented a new meta-learning approach to enable zero-shot AutoML. It leverages offline tuning experiences to learn data-dependent default configurations. So it can automatically recommend good configurations for a new task without tuning, pushing the AutoML cost to the lowest possible. For software impact, what profession benefits from FLAML? Based on our survey, the top 2 segments are data scientists and software engineers, followed by domain experts and machine learning researchers. Their programming experience varies in a large range. there are many internal and external use cases of FLAML in different application domains, like software development and engineering, security, banks, marketing, civil engineering, supply chain, insurance, and healthcare. In general, the impact of FLAML is in three folds: accuracy, productivity, and R&D. The models found by FLAML are successfully deployed in many products with high accuracy. FLAML saves huge amounts of dev time for both developers and data scientists. The ability to conveniently incorporate new algorithms into the existing pipeline, allowing easy extensions and being able to get large-scale parallel tuning makes FLAML play a big role in R&D of some big enterprise customers. To this audience, I also want to mention that the scientific impact is quite broad. I've seen scientists in very diverse domains using FLAML, like civil engineering, earth science and geology, chemical engineering, electrical engineering, finance, software engineering, databases, soil science. So experts in machine learning or artificial intelligence also have a good reason to use it. And that is to compare different methods or models more comprehensively with sufficient tuning of each method or model. How does FLAML fit in the ecosystem? It works well with popular open source machine learning libraries like scikit-learn, PyTorch, Hugging Face, as well as cloud services like AutoML. We had collaborations with other open source communities, including folks working in Anyscale and Databricks. We integrated FLAML with Ray for distributed hyperparameter tuning. We integrated with MLflow for logging, etc. We also have open collaborations with the academia. Our contributors are from all over the world. So FLAML has got thousands of stars on GitHub, and the Python library has got more than 500,000 downloads. I also want to mention that Microsoft offers multiple ways to do AutoML. For example, the core technology of FLAML is shipped in Visual Studio 2022 for .NET developers. It's ported to C# and integrated in ML.NET Model Builder. It's a tool in Visual Studio with a graphical interface. A developer without machine learning expertise can also easily use it to build a model from their own data and use the model in their application. Besides Model Builder, there are also code-first approaches to AutoML with ML.NET and C#. FLAML is the engine powering all these tools. FLAML gives a huge performance boost to the AutoML offering. For example, it greatly improves the number of models explored, reduces the timeout error rate by more than 50% with small time budget, and improve the accuracy significantly. For our future work, I'd like to highlight some open problems motivated by the lessons learned from our customers. Regarding the performance and customizability, here are some examples of open problems and research opportunities. For example, what's the most efficient approach to multi-output AutoML? How shall AutoML find models that generalize well over time? How to perform AutoML with multiple optimization metrics? And regarding the comprehensive end-to-end support, the open problems include how to incorporate deployment constraints into the AutoML loop efficiently, how to automatically find not only a model, but also a guardrail to a consumer. Can we estimate how long a given task takes AutoML to find the best model? Should AutoML include components to mitigate the undesirable ethics-related side effects of machine learning models? And how to design an AutoML system to incorporate the data collection step in the loop and inform users when to collect more data samples. So here are the references of my applications in the AutoML and hyperparameter tuning area. The bold ones are what I mentioned in this talk. So with that, so I hope you check our library on GitHub and read our papers and let us know what you think. So I'm very eager to hear feedback and also welcome to contribute in any form. And yeah, so I'm happy to take questions now.
Thank you, Dr. Wang, for giving a very detailed and insightful talk with the very latest technology you are developing and how it's being adopted. So we have some time for QA. People can directly unmute themselves and ask questions or post it to the chat.
Yeah, maybe I can give one question to start with. Well, I have many technical questions, but here what I think most relevant to this audience is that I think this sets a very good example of how this research contribution turn to like widely used software that has brought the impact. So what's your I'm wondering what's the main lessons you learned from this process? Like for example, I checked the GitHub repo and there's a lot of like new issues that you probably need to deal with on the daily basis. Right? How do you handle all of this?
Right. It's a fascinating like learning experience for me as well. Right. So in the beginning we just studied maybe some theoretical problems, try to develop a new method, new algorithm. But as we grow, we kind of grow from a very simple and prototype to a usable system. So yeah, along the process, there are a lot of learnings. So one, I can talk about a couple of lessons we learned, right? So the very first lesson I actually learned is from a failure of my earlier attempts to the AutoML problem, right? So if you look at the reference list here, right? If you look at the last one, so that was my like very first attempt to this AutoML problem, and it studied the slightly different problem than the hyperparameter optimization problem I mentioned in this talk, right? So that one is also a very interesting theoretical work. Like we proved, for example, if you have multiple models to select on large data set, how can you confidently pick the best model without using the full data, only using a small fraction of sample data? So that work itself is interesting. But the issue is then we find that the API, right, or the applicability of that technique is kind of restricted and not directly usable by most of the modern need of AutoML. So that's the first question. The API really matters, right? The primary interface. If your target is to have some users be able to leverage their technique, and keep in mind what they really need, and so try to solve the exact matching problem. So even a slight mismatch in the API could lead to unusable. Could differentiate between like very easy to use technology and hard to use technology. So that's one. And the second one is when we develop our project, it's very important to learn from customers about the problem they're facing, right? I mentioned a couple of them. For example, the customizability is probably something that many people didn't pay attention in the beginning. But as we worked with the diverse users, we found all sorts of different needs from them, and like the customizing metrics and so on. And this is reasonable because usually they want to optimize for some business metrics, right? Not just the model accuracy and so on. And the business metrics can vary from organization to organization, but that's really what they care. So you can't put like a seemingly beautiful model, but putting production is worse than before, even worse than the rule-based methods. That's something they can't take. So sorry, my head is disconnected. Can you hear me now?
Yeah.
So those issues, for example, raised by the users, some of them actually contains very valuable research ideas that have been overlooked. If we haven't worked with the real customers, we will never be able to understand those questions. So these are some lessons I learned during this journey.
Okay. Is there any other quick question? We are almost to the end of the time.
Yeah, and another thing I mentioned is really beneficial to have collaborators from different places which provide diverse perspectives. So diversity and inclusion is one important factor. So that's why I'm very happy to talk to this audience and see, see if we can find some common interest and build something together, for example. And we have learned how to collaborate with different open source communities as well when we build FLAML, like I mentioned earlier in my slide.
Okay. I think with this, we can conclude the seminar. And thanks a lot again, Dr. Wang, for your time and for the insightful presentation. Okay.
Yeah.
So let's give a big hand to Dr. Wang.
Yeah. Thank you all for your attention and for the questions and discussions. It's wonderful.
Thank you. Bye.
Thank you.
Thank you. Bye.